right, day 2 in our discussion of temperature and heat energy. And this is an important point I would like to make before we begin and pick up where we left off last Tuesday. And the important point is temperature and heat are not the same thing. This is a key misunderstanding in both chemistry and physics. I've even seen textbook definitions. When you look in the back of the textbook, when I was a high school teacher, I had my students define what is temperature. What is temperature? What I wanted them to say was temperature is a measure of the average speed of the movement of the particles of a substance. That was the definition I wanted. They looked in the back of their chemistry book. In the back of their chemistry book, it said temperature is a measure of heat. I went, oh no, until they all gave me that definition because that's what the book told them, right? Well, the book was incorrect. Temperature is not a measure of heat. And here's a metaphor or an analogy to hopefully give you that idea. If I had a cup of water, and that cup of water was 23 degrees Celsius, and I had a swimming pool of water, and the swimming pool of water was also 23 degrees Celsius, which one of those substances would contain more heat energy? The swimming pool or the cup, if they're both at 23 degrees? It's not the same. The pool is going to contain more energy because there's more particles of the substance in the pool, and each particle, by virtue of it having a temperature, is moving. And so if you have more particles moving, you have more heat energy. So clearly mass has something to do with the amount of heat energy something has in it. You have a cup of water at 23 degrees and a swimming pool of water at 23 degrees. The swimming pool is going to have more heat energy even though they're the same temperature because you've got more particles moving. All right, say for example, instead of swimming pool, if we were going to talk about perhaps 2 cups of water. If I take 2 different cups of water, each of them has 150 mils in each of the cups, and they both start at 23 degrees Celsius. And into each one, I'm going to add 10 mils of boiling water. And the boiling water is, we're in Chandler, so the boiling water is about 97 degrees Celsius. It doesn't get up to 100 in Chandler because we're a little above sea level. We'll talk about that in this chapter. Would you expect the temperature of both of these to rise by a consistent amount? That they would both rise 5 or 8 or 10 degrees? You would expect that because they're both the same volume to start with. They're starting at the same temperature and they are of the same substance. So now if it wasn't water and each one, how about if I had water and milk? Some water in one, still 150 mils, and I had milk in the other, it was also 150 mils. They both started out at 23 degrees Celsius. And into each of these containers I add 10 mils of boiling water. Now I don't expect you to predict which one would end up at a hotter temperature, but do you think that the temperatures would be the same, like if they were both water, or would they be different? They would absolutely be different. Why do you think they would be different? The substances are made of different molecules and different things that are inside of the substances, and it has a lot to do with how closely packed the molecules are as well as the size of the molecules. For example, if I had, we'll just call it substance A and substance B. Say substance A was a much smaller substance and the particles were much smaller, and say I only had 1 gram of that substance. If I had substance B and the particles were much bigger, even though I still had 1 gram of the substance, which one of those would have more pieces in it? A would have more pieces in it. If they both started out at the same exact temperature, 23 degrees Celsius, which one of those, based on the swimming pool cup metaphor, would have more energy? If they're both the same mass, they both start at the same temperature, which one would have more heat energy? A would, because once again, there's more particles. Although the mass is exactly the same, and in the metaphor with the cup and the pool, mass certainly makes a difference in amount of heat energy, but also the size of the particles makes a difference in how much heat energy a substance can contain at any temperature, as well as how much energy a substance can absorb. Now, we cannot measure heat energy directly. It is impossible. And you go, wait a minute. What about a thermometer? A thermometer measures temperature, but temperature is a measure of the average motion of the molecules. Just like we talked about in the exam curve in this class. If you look at any set of scores, in this case, the speed of molecules, when I take the temperature of a substance, Some of those molecules are going to be moving very slow. Some of them are going to be moving very fast. When I take the temperature, I'm taking the average, the smack dab in the middle of the slow versus the fast molecules, and somewhere in the middle is the large bulk of the molecules are moving at that temperature. And here's how I can prove that to you. If I had a cup of water and I set it out in Arizona in July, what would happen to that cup of water eventually? It would evaporate, but would it ever boil? No, it would not boil, but yet some of those particles would have enough energy to leave the surface as if they had boiled. So what that means is they're in every group of molecules, whether it's 23 degrees Celsius, 80 degrees Celsius, or 97 degrees Celsius, some component, some percentage of the molecules is going to have enough energy to leave the substance as a liquid. And at that point, if I took all the fastest moving molecules and I made them leave, what would happen to my overall average? The overall average would go down. It's just like in this class. If I took all the tallest people in this class and I made them leave, and then I recalculate the overall average height of everybody in this class, the overall average would go down because I took the tallest people out, right? That's what happens during evaporation. One of the labs that we do in Chem 130, we take a little bit of rubbing alcohol and we put it on our skin, and it feels very cool. Why does it feel cool when we put rubbing alcohol on our skin? What's evaporating? The rubbing alcohol. As it evaporates, it requires energy. Where is it getting that energy from? From you. Okay, so alcohol will evaporate on its own. There are some molecules that are moving fast enough, but we can speed that up and we can increase the percentage that will evaporate by simply heating it up, right? So evaporation is actually a cooling process. When things evaporate, the overall average of everything that's left over goes down because now all of a sudden you've taken the hottest moving ones and you've moved them out of the solution. There's a very famous equation that we use when we calculate heat energy transfer. Remember we talked about energy being one of three categories in this class. We have energy thermal, we have energy chemical, and we have energy phase change. So this is thermal energy, chemical energy, and phase change energy. Thermal energy is really easy to think about and talk about. That's like when you put your hand on something and it feels cold. Right now, I want you to take your hand and put it on a plastic part of your desk, and now put it on to the metal part of the leg of the desk. One hand on each one. Put one hand on the plastic, one hand on the metal. Which one of those substances feels colder? The metal feels colder. But what if I told you they are exactly the same temperature? I promise you. If we took a thermometer, we embedded it in the metal, we embedded it in the plastic and the metal would be at equilibrium. Everything in this room is at equilibrium in terms of its thermal distribution of the energy. So they are at the same temperature. If they are at the same temperature and you accept that premise, why does the metal feel cooler than the plastic?
It's absorbing water and heat.
Because what is the metal doing that the plastic is not doing? It's moving heat energy where? Away from your hand and into the metal. So it is a more efficient conduit of heat energy, the metal is, than the plastic. Well, that must have something to do with the nature of the substance that the metal is made of versus the plastic. And that's what this idea is here. When we look at Q, Q is energy. What are the units of energy? Joules, if we're talking about the metric units. What are the English units that are more commonly used in food preparation? Calories. All right, we're going to use joules in this class because we always use metric. A joule or a calorie is a packet of heat energy, like a penny or a nickel or a dime or a quarter. So I want you to start thinking about energy like money. I want you to think about them as dollars and cents. M must be what in this equation? Mass. And what kind of units do we measure mass in? Grams. We're going to skip CP for just a minute. And delta T is what? Change in. Anytime you see a delta before a symbol in science, whether it's physics or chemistry or anything else, it means change in. So it's the change in the temperature. So certainly temperature has something to do with the amount of energy that's going from one place to another. We cannot measure heat energy directly, but we can measure it moving from one place to another. So the mass certainly has an effect on it, like the cup versus the swimming pool metaphor. How much temperature change makes a difference in how much energy is moving. The last thing is this unit right here, which is called the specific heat capacity. And the units of specific heat capacity are joules per grams degree Celsius. Now there's a question, I don't want to go on before we answer the question. What's your question, hon?
So from Tuesday's lecture, there was an equation for kinetic energy. Are we going to know that as well?
You will, but not right yet.
Oh.
Okay. So our equation here that is you're going to be using throughout this chapter and beyond is this one right here, Q equals mc delta T. So you need to make sure that you can use this in all of its permutations, just like the density formula or the molarity formula. You need to be able to solve for any of the permutations of this particular thing. But before we go on to that, what I want to do is describe each of these things. All right, energy is these packets of energy we call joules or calories. Mass is how much is in the substance. The temperature, the delta T is how much temperature change is observed. It's not a positive or negative value, it's just the change in. This idea of specific heat has to do with the identity of the substance. Remember the metaphor with the milk versus the water? We said that if we poured the same amount of boiling water that they would definitely be different. Look at this table right now. This is called a table of heat capacities. This is specific heat and molar heat capacity. This value here is specific heat capacity. And this value here is what we call the molar heat capacity. Notice the units are different. The units both have energy as the numerator. So how much is it going to cost you? And the denominator for specific heat capacity is grams per degrees Kelvin, which is the same as degrees Celsius in this case. And the denominator here is moles per degree Kelvin. So let's look at this value first, because this is what's going to be super helpful. And this depends on what the substance is made of. Let's look at the things that we know that are common in our everyday lives. Let's look at something like some metal that you're used to. Let's look at copper. A little dot by copper, 0.385. Iron is 0.449. And I always like to throw aluminum in there because it's just an interesting number. So let's look at aluminum, copper, and iron. So if we take these from our sheet, aluminum. Oh, by the way, this is going to be the discussion that is your essay question is based on. So this is not just an introduction. This is actually information that you're going to need to know. We look at the specific heat capacity for each of those. Aluminum specific heat capacity is 0.897. See, copper's heat capacity, where the heck is copper? There we go, 0.385. And iron's heat capacity is 0.449. All right, I'm going to change the order of these just so it looks a little better. I'm going to put copper at the bottom, just so it gives us this nice graduated scale. And remember, the units are joules per grams degrees Celsius in each of these values. All right. This is a complex derived unit. This idea of joules per grams degrees Celsius. Remember, joules is our energy term. It means how much energy is required. In the denominator, it means per gram of that substance to change its temperature by 1 degree. So this is a measure of the heat energy necessary that you would have to add to 1 gram of that substance to change its temperature by 1 degree Celsius. Let's think about this like money. 89 cents versus 44 cents versus 38 cents. Which one is the largest dollar amount? 89, 44, or 38? 89. So aluminum costs you the most money or the most energy to warm up 1 gram of it and change its temperature by 1 degree Celsius. Iron's in the middle, and copper is the cheapie. Copper doesn't cost you as much energy to raise the temperature of copper. Well, let's think about what that might have to do with. Perhaps it has something to do with molar mass. Let's look on the periodic table. Aluminum's molar mass is, looks like, what is that?
26.98.
So we'll say 27 grams per mole. Iron's molar mass is 55.9 grams per mole. And copper's molar mass is 63.5. I see a trend there. What do you notice is the trend with those numerical values? They're opposite. They're inversely proportional. So let's think about why that's true. So something that has a lower molar mass is going to cost me more energy to warm it up. Something with a higher molar mass is going to cost me less energy to warm it up. Let's pretend I had 1 gram of each of these substances. This box represents 1 gram. With this molar mass, now think before you answer, that's how many grams 1 mole of that substance weighs. Which of these particles is going to be the largest? Which one is going to be the heaviest with the largest radius? Is it going to be aluminum, iron, or copper? Copper is going to be the biggest molecule, or the biggest atom, right? So if I wanted to depict copper atoms, my 1 gram of copper atoms, I'm going to depict them as relatively large spheres because the molar masses, they're pretty darn big, right? It looks like aluminum is about half the size. So I'm going to make some spheres that are about half the size in aluminum. What size of spheres would I use to represent iron? Somewhere in between, right? Iron is like the Goldilocks atom. Not too small, not too big, somewhere in the middle. All right, which one of those, if they all are 1 gram, they all have the same exact mass, which one is going to have more pieces in it? So the most pieces, this one has the least number of pieces. So then, with that idea in mind, why does it take more energy, almost twice as much energy to warm up a gram of aluminum than it does to warm up a gram of copper?
Heat up more pieces.
You have to heat up more pieces. More pieces absorb more energy. If each one of those pieces absorbs some vibrational energy, because they're all solids, right? We're talking about solids here. We're not changing them into liquids or gases. Each of these, aluminum, iron, and copper, are solids at room temperature, right? I want to warm them up, and if each piece takes some quanta of energy, I got to give each piece a penny. Which one is going to cost me more money to warm up? Something with a whole bunch of pieces or something with just a few pieces? If I got to give each piece a penny of energy, it's going to cost me the most to warm up something with a whole lot of pieces in it, right? Okay, so that has a whole lot to do with this idea here. So the density of the particles, how many particles there are in a substance, certainly what also makes a difference is solid, liquid, or gas. If we look at something like iodine gas is 0.145 compared to the specific heat capacities of these. So gases are much lower heat capacity. Let's look at water. The heat capacity, oh here, wait, I'm looking at the wrong numbers. These are the heat capacities of metals. Does anybody know what the heat capacity for water is? 4.18. All right, how does that compare to these values? 38 cents, 45 cents, 90 cents, $4.18. Why does water take you so much more energy to heat it up? There's a lot of pieces in there, but what else? Hydrogen bonding has a whole lot to do with it because of those molecules in there that are doing funny things. So water has this enormous heat requirement to heat it up. We call it a heat sink. Arizona and San Diego are about in the same latitude, but in the summertime in Arizona, it gets down to 85 at night and get up to 120 during the day. That's a 35-degree range. In San Diego, during the same time and at the same latitude, it gets down to 85 at night, only gets up to 95 during the day, and they have a 10-degree temperature range. What's different about San Diego versus us if we're in the same latitude? There's more water. It's all right there next to the ocean. So what's absorbing a lot of that heat energy? Water. So I would bet if you live near a lake, that would make your temperatures a little bit more moderate and temperate. Here's another good question for you. I was remodeling my back bathroom, and I decided I love copper. Copper's my favorite metal. I decided I wanted a copper bathtub. Have you ever seen those? The big legs? I want a copper bathtub. Most of the bathtubs that I've seen that I want are iron, and they are coated with a ceramic substance on the outside, you know, kind of with the big claws on the feet, and the bathtub that sits there, and you can sit there and, you know, soak to your heart's content. Most of those are made of iron, and they have a ceramic coating on the outside. Well, I wanted a copper bathtub. The iron ones were about $1,000 to $2,000. The copper one was over $5,000. And I went, okay, how badly do I want a copper bathtub? So I was looking at the manufacturer's claims, and here's what the manufacturer said. If you buy a copper bathtub compared to the iron counterpart, which is what the other ones with the ceramic coating are made out of, they're iron on the inside, our copper bathtub will keep your water warm longer. Is that true? Looking at the specific heat capacities of both metals, which one would it take more energy to warm up? 38 cents versus 45 cents. What's more? 38 cents versus 45 cents. Which one is more money? Oh, wait a minute. I'm thinking 89 cents. Hello, Lorelei. My mouth doesn't know what my brain is saying. Vice versa. You're right. Copper would require more or less energy to heat it up. Less energy to heat it up. But there's another way to think of this idea of specific heat. Specific heat also tells you how, and this is important to engineers, how readily that substance will transfer heat energy through it. So the higher the number is, the more energy it's going to take to heat it up. But the higher the number is, the better of a conduit it is to move energy from one place to another. So which one of those would be cooling off faster? The iron would, right? It would be moving that heat energy out of your bathtub and into the surrounding area. So was the manufacturer correct?
Yeah.
They were correct on this case, right? So the copper one, I don't know if it's worth $5,000. But certainly it does make a difference. So this is going to prove to be very helpful, this listing of molar heat capacities. All right, let's look at that in terms of some calculation values and what we might want to use. So I actually have, I'm not as good at making these things up off the fly as I am with all the other kind of calculations. So I picked some out in our textbook that we can use. All right, we're going to start with calorimetry because that's what we were talking about right now. First question. Let me see if I can zoom on this thing. Zoom, there we go. All right, first question. Two solid objects, A and B, are placed in boiling water and allowed to come to temperature there. I would say change the wording on this question to allowed to come to thermal equilibrium, meaning that the temperature of the water and the temperature of the metal at that point are exactly the same, right? So thermal equilibrium, they're exactly the same. Each of the pieces of metal is then lifted, and I'm assuming that they're different pieces of metal, and I'm also assuming that each one weighed the same amount of mass. That would only be fair, right? Okay. So each is then lifted out and placed into separate beakers containing 1,000 grams of water at 10 degrees. A increases the water by 3.5 degrees, where B increases the water by only 2.6. Which one of those things is going to have the larger heat capacity? Which one would have the higher value in this particular table here? Would it be A, that had the larger temperature increase, or B, that had a, looks like, lesser temperature increase? How many people think that A would have the larger specific heat capacity? How many people think that B would have the larger specific heat capacity? Well, I think I probably agree with the A people, right? Because remember that number, the larger the number, the better it is at moving heat energy from one place to another. And so if they're at the same temperature, it's going to be better at releasing that heat energy into the surrounding water than the counterpart that has a lower heat value. So if we look at the next one, the molar heat capacity of liquid water. So I have it up here. This thing, where's water? No, it's not that. Well, we won't go that problem then. Let me find one that's easier to manage. Hang on a second. I want a calorimetry problem that's easier with thermal energy. I had picked some. Here we go. Ah, here's a good one. All right, 5.47 we'll use. Specific heat of copper metal is 0.385 joules per grams degrees Celsius. All right, I'm going to take a piece of paper out. I'm going to copy some of this information down onto the problem. So our specific heat capacity is, for copper, is 0.385 joules per grams degrees Celsius is our CP. How many joules of heat are necessary to raise the temperature of a 1.42 kilogram block of copper from 25 to 88.5? So our temperature initial is 25.0, our temperature final is going to be 88.5. Alright, so I'm going to go back out of that. So zoom minus now. Alright, so there's our problem. So we take our copper metal, sample of copper, solid. We got 1.42 kilograms of it. There's our temperature initial, our temperature final, and we know that this is the algorithm that we like to use for this kind of a problem. Alright. Whoopsie. Well, based on that algorithm, what values do I have that I can simply plug and chug? Well, I got this, but in mass we had to have it in units of grams, so I'm going to take 1.42 kilograms, and what am I going to do with that? Change it into grams. I can't do it like you engineers do it. I got to do it on paper. So kilograms is bigger than a gram. There's 1,000 grams in a kilogram, so that's 1420 grams. All right. So my energy, which is Q, my Q term, is the mass. In this case, 1420 grams. What's my specific heat capacity for copper? 0.385. Make sure you always put your units in there. And what's my delta T?
63.5.
So the difference between those is 63.5 is my delta T. Somebody must have done that while we were waiting. 63.5 degrees Celsius. All right, well that's a pretty straightforward example of plug and chug. Now, when you go through and you multiply these numbers together, I always make sure I put my units. What are the units that cancel here? Celsius cancels and grams cancels. So what is my unit going to be in my answer? Joules. Somebody with a calculator, what is the answer for this?
34,715.45.
Okay, well if we did sig figs, what would we round this to? I would say 34.7, because it looks like 3 sig figs consistently to me on most of the information in the problem. All right. There used to be a lab that we did in this class. And here was similar to the lab. And let's just go through and we'll use this as a calculation example because it's one that we can say. All right, so you got boiling water. And say we have a hunk of aluminum in there, and we already decided what's our heat capacity for aluminum? It's like 0.8 something, isn't it? 0.897. This is actually interesting information about aluminum. Maybe some of you see some of those ads on TV, as seen on TV, and you can buy this thing and you get it at home and it does these miraculous things. There used to be a thing that you could buy on as seen on TV, and it was a block of metal, and you would take that block of metal and you could put a frozen steak on it, and it would thaw out your steak in 10 minutes or less, and it thawed out much faster than it would if it was just sitting on the kitchen counter. What do you suppose that block of metal was made out of? Aluminum. It has one of the highest heat capacities of all the metals. It's relatively cheap to manufacture, and you put a steak on it, a cold steak on a block of aluminum metal, aluminum, and here's your steak. The aluminum is going to be a conduit for heat energy from where? What's colder? Steak is colder, so which way is the energy going to be going through in the aluminum? Into the aluminum, and through the aluminum and into the steak, right? It's going to be a conduit for heat energy from the atmosphere. It's going to thaw out that steak a whole lot faster than anything else. So, got a block of aluminum at home, throw your steak on there and you'll thaw it out much quicker. Yes?
So is it higher the energy that it has, the quicker the temperature?
This value, this specific heat value, you have to think of it two ways. And like I said, this is super important to engineers. The first way you have to think about it is the amount of energy it takes to heat up that stuff. It costs a lot of energy to heat up aluminum, all right? A good way to think about that is when you put a baked potato in the oven and you wrap it in aluminum foil, right? There's a reason you wrap it in aluminum foil, because it's going to move that heat energy into the potato real quickly. Right? You also have to think about that number as it being a measure of how readily that substance will move heat energy from one place to another. Turns out aluminum is very efficient at moving heat energy from one place to another, because it absorbs a lot of energy, but it moves it also very rapidly, because there's so many pieces in there. There's so many pieces of stuff in aluminum. They're such small atoms that they can absorb a lot of energy because there's so many of them. Right? Okay. So we have a hunk of aluminum. We get it up to 97 degrees Celsius. And say the aluminum weighs we're going to make it be a little heavier. We're going to say it's 9.756 grams worth of aluminum. We take that aluminum out, we put it into a coffee cup calorimeter, right? So we're going to take that hot aluminum out, we're going to put it in the coffee cup calorimeter. The original temperature of the water in the coffee cup, you guys don't know what a coffee cup calorimeter is, so just a coffee cup. The temperature initial of the water, we'll say, was 23 degrees Celsius, which is my favorite number because that's about room temperature water. And after we put the aluminum in it, the temperature final of the water ends up being 25.5 degrees Celsius. All right? I want to know how much heat energy went into the water. Okay? So now we have to think about system versus surroundings, which is the super most important key part of chapter 5, is being able to define the system versus the surroundings. System versus surroundings you can quantify as energy moving from one place to another, but you still have to use Q equals MC delta T, and you have to keep the system and the surroundings information in that part of the problem. So for example, if I want to know the Q that went into the water, I want to know how much heat energy went into the water. Say I had 150 mils of water. How could I figure out how much heat energy went into my 150 mils of water? Okay, well if I got 150 mils and 1 mil is 1 gram, how many grams of water do I have? 150 grams, right? Specific heat of water we just described, which is 4.18 joules. Remember this enormous number compared to the specific heats of most metals, which is less than 1. Water has this enormous heat energy. And what's my last value? 2.5 degrees Celsius. All right, somebody with a calculator, what is my Q value here? 150 times 4.18 equals times 2.5 gives me? Yes?
How come we didn't use that 9.75?
Well, we're not there yet.
Okay.
We're not there yet. So what do we got here? Because we're just calculating the specific heat, or we're calculating the energy that went into the water. And certainly it came from the metal, but we're not using the metal in the calculations yet, because let's think about that. That's actually a really good question. Which way was Q going? When I put this hot metal into the cool water, which way was Q moving? From the aluminum into the water, right? So Q is going in that direction. So we want to quantify the surroundings. So the Q was the surroundings.
Okay, so we're just all for the surroundings, not the
Right, not the aluminum. So we want to know the Q that went into the surroundings that came out of the aluminum. So that's why we have to define system versus surroundings. So what is the Q value here?
1,567.5.
And what would my units be on this value?
joules.
Joules. Okay, so that's the energy that went into the water. What we have to assume is, where did that energy come from? The aluminum. So the aluminum carried this quanta of energy with it. And where did it get that quanta of energy from?
The hot water?
The boiling water. So it scooped up some of that energy, it held it in its molecular structure, and then when you put it into the cool water, what did it do with that energy? It released it. So initially, this water was at 97, I had 9.756 grams of it. If I did not know what the specific heat of copper was, I could actually calculate it. I could calculate the specific heat of copper, because if we assume that the Q that came and went into the water came out of the metal, wouldn't that give us this? That says, okay, if this is the Q that came out of the metal that went also into the water, we could say the Q of the metal is equal to the Q of the water. Wouldn't that be the exact same joules? That the amount of joules that the metal took out of the water, the boiling water, it then released when it went into the cool water. Wouldn't those Q values be exactly the same? Right? So the Q of the metal has to be the Q that went in. So in this system, in this case, the Q was going into the metal, and in this case, the Q was coming out of the metal. Right? So you have to think about the system versus the surroundings. In this case, the Q is going into the system from the surroundings, and in this case, the Q is going from the system out into the surroundings. So it was going in opposite directions each way. We could calculate the specific heat. If this is true, then we could say the MC delta T of the metal is equal to the MC delta T of the water, right? And didn't we just calculate the MC delta T of the water, which is this number, 1567 joules, would have to equal 1567 joules here. If I knew the mass of the metal, right, 9.756 grams, and I knew, let's see, well, the temperature change is going to be hard to calculate, but I could get that information, I could know the specific heat of my metal, and then I could calculate the energy that went through. So either way, we'd have to have some more information to calculate the specific heat of the metals, namely appropriate mass of the metal that I just didn't make up from out of my head. All right, let's do another kind of these problems out of the textbook. All right, here's some where, actually, you know what, before we even go on to more problems, let's look at enthalpy in general, this term enthalpy. What we just calculated was enthalpy. This is a term that you have not talked about before. Enthalpy is the total energy transferred. It could be energy chemical, it could be energy thermal, it could be energy phase change. So enthalpy is any kind of energy that you transfer from one place to another. Substances also contain a particular enthalpy just by virtue of their creation on the planet. And that's what this table is that I gave you in class. This is in the back of your textbook, but I copied it for you because we're going to be using it to do some calculations, and you're going to need it for calculations in your homework. The values that you're going to be looking at in this table is the delta H values. Delta H is the enthalpy change. Meaning energy had to either go into or out of that substance in order for it to come into existence in the universe. So for example, if we look at some of these substances, these are values you're going to use in 152, so we're not really going to use delta G or S values. In this class we focus on delta H values. So if we look at all the enthalpies, this is the amount of energy it takes to either create that substance or the amount of energy that's released when that substance is created. So if the value is a negative value, that means you had to put energy in to make that thing exist. So aluminum chloride took 705 kilojoules to make 1 mole of it. Aluminum oxide takes 1,669 joules for it to happen. Other values you see are positive values. That means when that one comes into existence, it releases that energy into the universe. There are some enthalpies with 0. What are the ones that are 0? Look at the ones that are 0. What are the enthalpies that are 0? All solid what? What kind of things that are solid have a 0 enthalpy? Elements that are metals. So any metal, just like any metal that is in redox reactions, has a 0 charge. Any metal solid state has a 0 enthalpy, meaning it doesn't cost the universe any energy to make it. It doesn't get any energy back when it is made. What else also has an enthalpy of 0? Gaseous things that are what? Diatomic. So all the diatomics have enthalpies of 0. So you're going to use these in order to do some calculations based on enthalpies of reactions. So let's see. I think there's an example in the PowerPoint here of this. All right, we already talked about these things.
It's so funny how like 2 examples we talk through all of this.
So here we go. Here's a good enthalpy value change. This is the table that I gave you is called heats of formation table. So we're going to use this heats of formation to calculate the enthalpy change that happens. And in order to, and this is table 5.3 in your book, but it's also in your textbook at the end. And let's see if they give us, here we go. Delta H is the enthalpy of the products minus the enthalpy of the reactants. So there's the algorithm that you need. The enthalpy of the products minus the enthalpy of the reactants. So let's practice that into some practical application. So what we're looking at in this reaction is this particular chemical reaction here. What does this look like to you, this reaction? What kind of reaction is this? It's a decomposition reaction. So we're taking something that's a solid and we're breaking it up into smaller components, one of which is a solid and one of which is CO2 as a gas. So if we look at that information, let's think about what's actually happening here on a, oh, this is not a good example. Well, let's calculate enthalpy and we'll go back to this example in a minute. So we want to look at the enthalpy of the products minus the enthalpy of the reaction. So the overall enthalpy change, which means there's got to be energy going into this system or energy coming out of this system overall. In Chem 130, they told you this is exothermic or endothermic. It's going to get warmer or it's going to get colder. So the delta H is equal to the enthalpy of the products minus the enthalpy of the reactant. So let's look up the enthalpy of calcium oxide. So what you have to do is you're going to look in your table of values for the products. So there's our chemical reaction. Zoom out here a little bit better. There's our chemical reaction. So now we're going to look at our table of enthalpies. And what does your table of enthalpies tell you? All right. If we look at calcium oxide, we have to look up the right chemical. Calcium oxide as a solid. So we look at calcium oxide as a solid. The value for the enthalpy change is negative 635.5. All right, so what I'm going to do is calculate the enthalpy change is negative 635.5, and the units are kilojoules per mole. So kilojoules per mole. So that's one of the products. So the enthalpy of the products, but that's not the only product. I have to look up CO2 gas. So we go back to our table of enthalpies. We look up carbon, which is probably connected somewhere to CO2. There we are. CO2 gas has an enthalpy change or enthalpy of negative 393.5. All right. So plus negative 393 point, extend this onto another piece of paper, 5 kilojoules per mole, right? So there's my enthalpy of the products. Now I have to subtract, I should have done this all in one long line, the enthalpy of the reactants, which is calcium carbonate. So once again, we look back at our table of enthalpies. Calcium carbonate, is it a solid in our equation? Yes, it is. Calcium carbonate, negative 1207.1. So I'm going to take you can't see it? I'm sorry. You know what? I'm not paying attention to this. All right, negative 343.5 minus the enthalpy of calcium carbonate, which is negative 1207.1. So now you have to do some algebra with this, right? When you subtract a negative number, what you're actually doing is what? Adding. So what's this? What's negative 635 plus negative 343? What's the solution to that part of the problem? Could be 9 something, right?
48.
Exactly. Plus 1207, right? Because negative minus a negative gives you a plus. So what does that tell you? At the end. See if we come up to the right answer.
228.
Ah, they wanted us to do it the opposite way. They wanted us to calculate the calcium carbonate. That's okay. What we did here was, what was our answer? 228. Let me go back to the ladybug. So this would be how we would calculate 228.1 kilojoules per mole. That's the enthalpy for the whole reaction, right? That problem wanted you to do a little bit more algebra. They wanted to calculate this one based on giving you the overall enthalpy and the individual ones, but this is how we would calculate the overall enthalpy for that reaction. Yes?
I understand everything. I'm just trying to figure out where that plus came from. Is that from the CAO plus the
Based
CO2?
on my original algorithm, that I have to combine all of the enthalpies of the products.
Yeah.
So each one of those is going to have their very own enthalpy, and I have to combine them together, right, to get the enthalpy of the products minus the enthalpy of the reactants. In this case, we have one reactant and two products. If you had the reverse reaction, for example, you had a combination reaction, you would have two reactants and one product. So you just have to combine the enthalpies of all the things together. Let's do another problem like that, because this is in your homework. And I think this will give us a little bit better of a perspective. I like this equation. I'm going to write this a little bit differently. And I like the way that they show this. This is what they call an energy diagram. And what this energy diagram is showing you is that which energy is higher? This energy? Is this energy higher? Or is this energy higher? Which one of these things has more energy? The stuff up here or the stuff down here? The stuff that's higher, right? If enthalpy or enthalpy is increasing along that vertical axis, right? Here's our axis. Enthalpy is increasing, so these must be at a higher energy level. So if we were going to write this particular equation, we could say, all right, CH4 as a gas, I'm going to write it up here so you guys can, CH4 as a gas, plus, I will in a minute, 2O2 as a gas yields CO2 as a gas plus 2H2O as a liquid. All right, if I look at it that way, if I look at it using these as the reactants, right, and these as the products, which one of these enthalpies would I use? If I'm saying these are the reactants and these are the products, which enthalpy would I use? The negative 890 or the positive 890? The negative 890. So when I go to depict that in my chemical equation here, see, I put these as the reactants, there's the products. I would then put my overall enthalpy change as the negative, what was the value? 890?
Yeah,
Negative 890 kilojoules per mole. Now that turns out to be a super important idea here. This negative sign means that it's, does that mean it's exothermic or does that mean that it's endothermic? Exothermic. So a negative value, so and this is super important, commit this to memory. Negative delta H value means it's an exothermic reaction. What does exothermic mean? In Chem 130 they told you the stuff gets hotter. No, that's not what it means. What exothermic means is that you have a system and surroundings. Exothermic means energy is going from the system into the surroundings, so the Q is moving from whatever chemicals that you have into the water that is surrounding it. So system versus surroundings, a negative delta H means it's an exothermic reaction, That Q is going from the system into the surroundings if it's Q. Now if we reverse this reaction, and I write it in the opposite way, and I say CO2 as a gas plus 2 H2Os as a liquid yields CH4 as a gas plus 2 O2s as a gas. Now how will I write my enthalpy value? It's not negative anymore, it's positive, and that is true of all reactions. You can simply reverse the reaction. The energy term retains its magnitude. What changes is simply the sign of the energy term. So now we have a positive 890 kilojoules per mole. Now I want to make a comparison to what the textbook authors are using as this energy diagram. All right. If we go the forward reaction, the CH4 plus the 2O2 yields CO2 to 2H2O. It's an exothermic reaction. What they're showing you here is that the reactants have more potential energy stored in their bonds than the products do. And the amount of energy that's different is this 890 kilojoules that was released when the reactants change from being reactants to products. So energy is released from this system into the surroundings. If we go the reverse of the reaction, we take CO2 and H2O and we make CH4 and 2O2 out of it, it requires energy. So these things are starting at a lower energy level. They have less potential energy in their bonds when they're broken than these do once they're contained. So let me make that metaphor an idea simple. This idea of energy being released versus energy being absorbed is something that we like to talk about. Yes?
So would that make a positive change in H endothermic?
Thank you for asking that. Yes, positive delta H going to mean that it's endothermic. And in Chem 130 they said it gets colder, but that's not the case. What that really means is that an endothermic reaction is going from the surroundings back into the system. Right, so Q is going in the opposite direction. It's going from the surroundings into the system. And that's why it may feel like it's getting colder. All right, let's see here. Oh, here's the metaphor that I like to use in this. All right, say we're starting a cupcake company. This is the Hess's law idea. So this is my version of Hess's law. Okay? Say we're starting a cupcake company. And I make these amazing red velvet cupcakes. Everybody loves my red velvet cupcakes. And they're like, Lorelei, you need to start a cupcake factory in your spare time when you retire. Okay. So I got to get a brick and mortar place to make my cupcakes. I got to get the bowls and the mixers, and I got to buy lots of ingredients. I got to buy a sign. I have to have employees. So when I'm a startup business, we have expenses versus profits. Right? All right, so startup business, my expenses are huge. Very large numbers. Got to put a lot of money into the situation because my expenses are huge. I don't sell a whole lot of cupcakes right off the bat because nobody knows me. And so my profits are kind of small. So my overall change in my monetary situation, am I going to be putting a lot of money in or am I going to be getting a lot of money out? So my overall change is positive, meaning it's endothermic. I have to put money in order to get this thing to work, right? So I'm the system. I have to put money into the surroundings to get it to work. Well, then I've been in business for a while, right? And now my expenses are minimal because I have all the mixing equipment, I have my brick and mortar, I have my signs, I have all the stuff I need. So my expenses are small, but now everybody's discovered my red velvet cupcakes. They're like, dang, Lorelei, those cupcakes are awesome. And I'm selling them as fast as I can make them. So now what's my overall enthalpy change? Negative. I'm going to be making money. So money is coming out of the system and into the surroundings, right? I'm going to be spreading the wealth all over the place. That's what happens in chemical reactions. Sometimes it costs you a whole lot of money to break up the bonds, and you only get a little bit stored in the new bonds that are formed, and in that case, all that extra energy goes out and it feels like it's getting hotter. Other cases, You don't need to put a whole lot of energy in to break the bonds of the reactants, but then a whole lot more energy gets stored, and some of that energy has to get pulled from the surroundings into the new bonds that are formed. And so you have an endothermic reaction. So that's my metaphor for understanding Hess's law. So now if we go back into the PowerPoint and use the example, and let's actually, you know what? Let's calculate the enthalpy of this particular thing and see if it actually comes out to the positive 890. So you guys got your table of enthalpies there. I'm going to calculate the enthalpy of formation for this whole reaction. So what's CH4 gas enthalpy? Somebody look it up. CH4 gas. You got to look under carbon.
52.3.
Is it negative or positive?
Positive.
52.3?
Oh wait. Oh, my bad.
Negative.
Okay, so we'll try again. Delta H. So let's do CH4. So what is CH4?
Negative 74.8.
74.8 kilojoules per mole. All right. I have to add that. Now we got a tricky situation here. What's O2's enthalpy? 0. But had it had an enthalpy, I would have to multiply that enthalpy by the coefficient because there's twice as many of them. See what I mean? See where I got that 2? And even though it's 0, I'm still going to put it there so that you get the idea and you understand. All right, so there's that minus the enthalpy of the reactants. What's CO2's enthalpy?
Negative 393.4.
Plus, what's H2O as a liquid? It's different than H2O as a gas or a solid, so look up the enthalpy of H2O liquid.
Negative 285.83.
8. All right. Close those brackets. So now, delta H should equal what number? Positive 890 kilojoules per mole. So that's how you calculate the enthalpy of a reaction. Now, oh, wait a minute. You know what? I messed up. Where's my 2 H2Os? Nobody caught that. Bad teacher. There's a 2 there. You docked my pay on that one. My big bucks that I'm making. So don't forget to multiply by 2 like I did, right? Because you got 2 of those waters. And so if the enthalpy of a single water is negative 285, you're making 2 of them, you got to have double the enthalpy. Yes? I'm sorry.
No, you're good. I just want to make sure.
Yes. This one?
Thank you.
You bet. All right, let's do some more. Let's do some more. Still got 6 minutes of my time. Want to make sure that you know what you're doing here. All right, enthalpy problems. You know what? Let's go to some solution enthalpy. What we've talked about so far is we did a little bit of thermal energy exchange with specific heat capacity, Q equals MC delta T, mass, change in temperature, specific heat. You can maybe calculate those. You can calculate individual enthalpies. Now let's calculate some energy chemical enthalpies when you break stuff up in solution. So, for example, we're going to start with 5.34. So here's our reaction. CH3OH. I would suggest, if you don't have a textbook, that you write these problems down. So we got CH3OH as a gas, yield CO as a gas, plus 2H2 as a gas, and it gives us our enthalpy value of plus 90.7 kilojoules, and I like to think about it as kilojoules per mole. All right, they're asking you. There's our reaction. All right, the first question. Is heat absorbed or evolved during this reaction? So is it exothermic or endothermic? Endothermic. So would it get colder or would it get hotter? It get colder because energy is going from surroundings into the system. So in this case, what you have to think about is the system is this stuff breaking up into those things. So it costs you some energy to break those bonds up, right? You get some energy contained in those bonds once those things formed, but the difference between them is positive. So it must have cost you a whole lot more energy to break these up than what you got stored in those because the overall enthalpy is positive. B says calculate the amount of heat energy transferred when 1.60 kilograms. So we got 1.60 kilograms of that stuff are decomposed by this reaction at constant temperature. All right, so let's go through and look at this. And here's how I like to think about these kind of problems. And they don't always give you this in here. I like to think about it as, they always tell you the enthalpy is in kilojoules. I like to think about it as kilojoules per mole, because that gives you that compound unit that you can use to make some comparisons of. Well, we've got kilograms here, which is a mass unit, and we've got kilojoules, which is an energy term, and moles, which is number of pieces. How can we connect our mass unit to either energy or number of pieces? Moles of that stuff. All right. If you here's a universal method for solving chemistry problems. If you encounter a chemistry problem, whether it's in this class, on the MCAT, the GRE, the PCAT, whatever it is, and you say, "Yep, that's a chemistry problem. I have no idea how to solve it." The very first thing I want you to do is find something you can convert to moles. Best way to approach any chemistry problem, probably 90 to 95% of every chemistry problem, at some point you're going to have to find moles. Once you find moles, then the next thing you look at is the balanced chemical equation. So those two pieces of information will help you strategize solving any chemistry problem. Convert to moles and look at the balanced equation. Right now, commit that to memory. Convert to moles, look at the balanced equation. All right, so what can we get moles out of here? I think I get some moles of this stuff, right? Using the molar mass. So if I got 1.60 kilograms, I probably need grams out of that. So I've got 1600 grams of CH3OH. With that information, what can I do? Convert to moles. And what would I need in order to convert to moles? Molar mass. So 1600 grams of CH3OH, and I want to go from grams of CH3OH to moles of CH3OH. And 1 mole of that stuff, let's see, carbon is 12, there's 4 hydrogens, oxygen is 16, so that's 32 grams per mole. Somebody with a calculator, what's 1600 divided by 32? We're going to get a nice round number, like 200 or something. What is it? 50. Okay, I knew it was going to be a nice round number. 50 moles of CH3OH. All right, well, if I know how many moles I have and they want energy, doesn't this term connect number of pieces to energy? So all of a sudden, I just take my 50 moles, and now I'm going to put, now if I'm using 90.7 kilojoules, when they say kilojoules per mole, what are they saying? How many moles are they talking about? 1 mole. So I could use it like that, or I could use 1 mole is equal to 90.7 kilojoules. Which one am I going to use? I like this one. 90.7 kilojoules in 1 mole of this stuff gives me, what's 50 times 90.7? What would my units be here? Kilojoules. So that's how much energy is absorbed or released? Absorbed. Very good. So 4,535 kilojoules of energy would be absorbed when 1.60 kilojoules of this went through. Now, let me ask one more thing. This is important. If, in fact, I was looking at hydrogen instead, if I had the 2 hydrogen, and instead of this, I said I got 1.60 grams of hydrogen, and I wanted to convert that, I would convert to moles first, right? I'm just going to make up some number, say I have 32 moles of hydrogen gas. Now, when I convert that and I use this energy term, because there is a 2 there, I have to put the 2 moles of hydrogen gas is 90.7 kilojoules. And that's because for 1 run through this, this is the value, but in one run through, I get 2 moles of hydrogen gas, so we actually have to put the 2 down there, and that will take care of the homework that you have to do.
So what if it did just give us that CH3OH kilogram value and did ask us to find joules for H2? Would we just be able to find the moles, use a mole ratio, and then from there
You could. You could.
So if we did use that more ratio, would we still need that 2 more under the 94.7?
If you attach it to the energy term. Only that 2 goes there when you attach it to the energy term. If you're looking at the balanced equation is still the balanced equation. You don't change anything about that. But you can attach that energy term to that. Now, I'm going to encourage you all, read chapter 5, by golly. This all probably seems like a bunch of gobbledygook. You need to get in there and read the darn textbook. This is a chapter you need to read. Need to